The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, some of you will recognize this molecule that I have rotating up on the screen because it's one of the coordination complexes of Werner that we talked about last time. And Werner, of course, was well known, and some of you probably read his biography over the last few days on the Nobel Prize website. Well known for his theory that broke down the preconceived notions that had been prevailing at that time concerning the structure of systems that have unusual salt-like behavior in some cases, but that contain the 3D elements. I'm focusing on 3D, but this is also true of 4D and 5D elements, the transition metals, elements like titanium, vanadium, chromium, iron, cobalt, nickel, etc. And so this molecule here that you see spinning up on the screen is being represented here on the screen in one of these kind of arbitrary forms, wherein the cobalt center at the middle of the molecule is just a round ball of an arbitrary size, and then this particular molecule, which contains a cobalt-3 ion, is surrounded by a complement of 6 ligands. We have 3 chloride ligands that, because this program chose to do so, it colored those chlorides the same as the cobalt, not what I would do. And it put the ammonia ligands, 3 ammonia ligands around it, colored the ammonia nitrogens in dark blue and the ammonia hydrogens in white. And we talked about the fact that these transition elements, in fact, these 3+ ions of metals like cobalt, can behave simultaneously as Lewis acids toward a multitude of Lewis bases, here 6. Okay, so this is a times 6 Lewis acid in the middle, and 6 Lewis bases, which are 3 chloride ions and 3 ammonia molecules oriented around it in an arrangement that is quasi-octahedral, because the positions of the 3 nitrogens of the ammonias that are interacting with the cobalt center and the 3 chloride ions are located near the vertices of a regular octahedron. Okay, so we will be taking use of the geometry of molecules like this in discussing electronic structure properties of these molecules today. We'll be doing that beginning today, and that'll be important to understanding the magnetism and the color and also the reactions of molecules like this. Now, one other arbitrary thing that this program did is it chose not to draw lines between the cobalt and any of the 6 ligands. But normally when you see these molecules drawn in textbooks, you'll see that the lines drawn are the same as the lines between the nitrogens and these hydrogens. So we would have to add 6 more lines to this drawing to get the typical textbook representation of a molecule like this. But still, that would be a somewhat arbitrary representation. And so I would like to show you a less arbitrary representation. And we'll do that forthwith. And this one has to do with looking at the same molecule, but represented as an electron density isosurface. And that isosurface will be colored according to this function that tells us about the propensity to pair electrons in 3D space. And so you'll recall that when we talk about coloring electron density isosurfaces in this way, so this is now a physically important kind of representation of this coordination complex. This color scale will run from red all the way up to blue, and at blue is where you find regions in space where you're most likely to find pairs of electrons, okay, mapped onto the value here, color mapped onto the value of an electron density isosurface. Here, the value of the electron density that is present for every point represented on this surface is 0.11 electrons per unit volume. And so what you see here is that In fact, the electron density does become low as you move from the cobalt in the direction of any one of the ligands. But the lone pair on each ammonia is certainly polarized in the direction of the cobalt center. And the cobalt center is not uniform in terms of the way that electron density is organized around it. You see that right on the metal center, we see red, and then sort of at the corners of a cube, you see this yellow or green color on the cobalt. And that's very significant, and what we're going to be doing today is we're going to try to understand what happens when you put a set of ligands into an octahedral array around a central metal ion that has d electrons and d orbitals to play with. Okay? And in fact, what you'll see is that the oxidation state of the cobalt center here is +3. That's why I'm referring to it as a cobalt +3 ion. And because cobalt's in group 9 of the periodic table, you then know that there are 6 valence electrons on the cobalt center that you have to put into orbitals. And so what we're really seeking to know is, how can we get an energy level diagram for a system like this? And so we'll know how to put those 6 electrons into that diagram, the ones that are mostly localized on the cobalt, and make predictions about whether the electrons should be paired up or not, for example. So we saw with homonuclear diatomics, like the dioxygen molecule, that the electrons aren't all paired up. 2 of the electrons are unpaired. And when we have 6 electrons to put into an energy level diagram for the cobalt ion, we're going to wonder just what's the case. How many energy levels are there, and where do we put the electrons? And so we're going to need to very briefly review what I did at end of lecture last time. And that has to do with the properties of the 5d orbitals, because in order to answer the kinds of questions that we're posing about energy levels of metal ions that are transition metals, we're going to really need to know very well the nodal properties of these d orbitals. And so remember the m quantum number here can be 0 for the dz squared. It can be +1 for the dxz, and +2 for the dx squared minus y squared, -1 for the dyz orbital, and -2 for the dxy orbital. And let's draw those. dz squared is an interesting one, and because it's distinct from the other 4 d orbitals, we're going to be spending more time on it today than the others. What it has, these are the x, let's say y and z axes here, is it has a positive lobe along both plus and minus z. So it looks like a p orbital so far, except that we have the same sign both in plus and minus z. And then what we have is a very interesting toroidal shape that goes around in the xy plane all the way around in a cylindrically symmetric manner. And so if you were to look down z onto this orbital, it might look something like this. Like that. Okay, so it would be cylindrically symmetric about z. And that's another feature that I didn't get to add to this diagram at the end of last hour, which is that because of this property, this m equals 0, that means this is a sigma orbital with respect to the z-axis. Okay? Cylindrically symmetric about z. And then let's go to the xz, since I'm making this x, y, and z over here. The dxz has 4 lobes, and they are in between the x and z axes, as I'm trying to represent here. Okay. So these 2 are kind of coming out in front here, and these 2 back behind. And then the phases go as follows. So unshaded is again plus. And then we have the x squared minus y squared orbital. the x squared minus y squared orbital has 4 lobes. In fact, the shape of xz, x squared minus y squared, yz, and xy are all the same. It's just that they point in different directions in space with respect to the Cartesian coordinate axes. X squared minus y squared, like dz squared, is an orbital whose lobes point along the coordinate axes. Like this. And it's minus along y, as the name suggests, and plus along x, as the name suggests. So that's your dx squared minus y squared orbital. And then yz is like xz, but let me finish this part here. If dz squared is sigma with respect to z, and you imagine looking down z onto dxz, what would that be with respect to z? Anyone? Pi. Thank you. That would be pi with respect to z, because the yz plane is a nodal surface for this d orbital, as is the xy plane. And that's what we're trying to do here, is become familiar with these nodal surfaces. And accordingly, now if you look down z onto the dxy orbital, sorry, the dx squared minus y squared orbital, you're now going to see 2 nodal surfaces when you look down it that way, because you're going to see that there's one located over here that is a plane that contains the z-axis, but it bisects the x and y axes. And then there's another one over here, but that's 90 degrees to the first one. And that makes this one delta with respect to z. Okay? So delta is when you have 2 nodes that contain the z-axis, and if we're looking down that z-axis. And then over here, the dyz orbital has its 4 lobes between y and z, like that. And it is positive between y and z, and negative over here as I'm shading. Okay? And this one, like dxz, is pi with respect to z. And then over here we have the dxy orbital as our final orbital. And what you might be able to guess, we've got a sigma with respect to z. We've got a pair of pi with respect to z for m equals plus and minus 1. We also must have a pair of delta with respect to z for m equals plus and minus 2. And that means that the dxy orbital, like dx squared minus y squared, must lie in the xy plane. And in order to be orthogonal to dx squared minus y squared, we're going to have to rotate it such that its 4 lobes point now between the x and y Cartesian coordinate axes, like this. Although, try to improve on that with my coloration. But that's like that. So again, this is an orbital perpendicular to z, and which has delta symmetry. And now the 2 nodal nodes are in fact the xz and yz coordinate axes. Okay, so indicating those nodal planes there. All right? So this is certainly the basics for what you need to know about the d orbitals. And just briefly, I'd like to switch to the Athena terminal here to show you that there are ways for you to go ahead and visualize the orbitals, and I'm going to make this information available to you so that you can go ahead and do this yourself in order to visualize these in a way that will take you right from the equations for the orbitals to their graphical representation. I think that's really important to get a good understanding of orbitals. Let's zoom this a little bit so that you can begin to see it. Okay, this is a worksheet put together that in fact contains all the functional forms for the d orbitals. Let me see, where's that? There we go. And you can look at this with Maple on Athena, and then you can look at the equation that represents the angular part of the wave function for the orbital that you're interested in, and then you can go ahead and plot it, and you can plot it in such a way that the function is animated, and rather than just seeing it projected on a board as well as I can draw, you'll be able to see it drawn up graphically. In fact, these come from the solution for the Schrodinger equation for the hydrogen atom, and the angular part of these wave functions that's going to be oh so important to us is something known as the set of spherical harmonic equations. Okay, and that should reference you to this issue of standing waves that we have discussed. So let's just see what we can do here. Sometimes I'm not so good at using Maple up in front of the class. So. Okay, so what you're seeing is some of we're getting representations for dz squared. So right here is a way of writing dz squared. Okay, you're going to see an important term here, 3 cosine squared theta minus 1, and we'll come back to that in a moment. That's the angular part of the dz squared wave function. And then we can look at some of these other ones. You'll see that some of the d orbitals come as combinations of real and imaginary functions that are the solutions to the differential form of the Schrodinger equation, and then we take linear combinations of these to get real forms so that we can get plots that we can look at. And let's see if we can get dz squared here. There it is. Okay, so there's a picture of dz squared. And you see that if you're using this Maple worksheet, you can actually rotate that around and animate it a little bit. So you see that we have this torus that is in the xy plane, and you have the 2 large lobes that extend up along plus and minus z. Okay? And so I'm going to encourage you to go ahead and look at that worksheet, which will be available from our website, and to go ahead and look at some of the functions. And if some of you are interested in higher orbitals, the f orbitals are also available in this worksheet. So you can visualize the f orbitals that are important for understanding the chemistry of elements like, for example, uranium, okay, which have it's a little bit beyond the scope of 511.2. But now let's switch to the document camera. And if you could, I'd like you to make this part big. Okay, so this is a table in your textbook that has the angular part of the wave functions for various hydrogen-like orbitals. And this is the part I'm most interested in over here. Christine, if you could just focus in on the d orbitals over here. Okay, so when I was talking about the dz squared orbital a moment ago, I was focusing on this term here, this cosine squared theta minus 1 term. Okay, and then here are the other d orbitals. So these are the descriptors for the d orbitals, x, y, y, z, x, z, x squared minus y squared, and z squared. Okay, and I'll need to refer to this in a moment, so we'll leave this up. The reason why I have this arrow written into my book here is because these are backwards in the text. This one is actually x squared minus y squared, and this one is actually the xy orbital. So we figured that out last year when we were doing this lecture. And so your book isn't always right. You should make sure you check. And that's the same is certainly true of your instructor here. So, but we'll try not to mislead you. And so now, here's the approach that we're going to take. Let's say that we have our coordinate system, and we want to know how to evaluate one of these d orbital wave functions for a particular point in space. Actually, we're going to want to evaluate the square of the wave function. And so we're going to make use of a Cartesian coordinate system, and we're going to express things in terms of polar coordinates. Okay, so here's a sphere projected onto our Cartesian coordinate system. And some of you will be very familiar with this, but we're going to say, okay, if you're at a point here in space, then we can describe that point in space by a set of variables, which will be r, theta, and phi. And here's our angle theta. And if we drop down to a perpendicular on the xy plane from our point, then we're going to define phi as being from the x-axis and going over in the direction of y. Okay? And so when you look at the d orbital wave functions, you see that they are all written here in terms of just theta and phi, and not in terms of r, which is this distance here from the nucleus, from the center of this metal ion that we're talking about. Okay, so this would be the r. And what we're going to do is, if this point on the surface of our sphere represents one of our ligand atoms, so think back to that complex we were describing a few moments ago, cobalt with 3 ammonia ligands and 3 chloride ligands. We're going to approximate each of those 6 ligands by a point on the surface of our sphere. And then we're going to say, if there's a metal at the center, that cobalt ion in particular, what's the probability of finding a d electron where that ligand atom is? Okay? And in order to do that, we're going to need to be able to evaluate the wave function. And we're making the assumption for simplicity that this is a perfect sphere, and also that our coordination geometry is a perfect octahedron. And so we're not going to consider r, because r is going to be the same everywhere. It's just a perfect sphere with one value of r, no matter which ligand position we're looking at. And so that means we can focus in just on these, which are the angular part of the wave function for the molecule in question. And so let's see what this means with respect to dz squared. So the probability of finding an electron at some point in space in a particular atomic orbital is proportional to the square of that atomic orbital at that point in space. That's our probability density. We encountered that very early in the semester. And now we're going to make use of that to make a plot. We're going to plot this probability density of finding an electron in dz squared as a function of theta. Why can I do that ignoring phi? Well, that's because if you look at dz squared, there's no phi in that equation. Why is that? That's because dz squared is cylindrically symmetric about z. And look how we defined phi. It's as you go in the xy plane around starting from x. Okay? So that because of the sigma symmetry of dz squared with respect to z, there's no phi dependence of this wave function. And that should appear here in the angular form of the description of the dz squared orbital. And so now, but we do know that dz squared does depend on theta, because theta starts out somewhere here along, let's say, initially, theta equals 0 would be right on the positive z-axis. And then as we keep a constant r and we sweep down here toward the xy plane, the dz squared probability density is dropping off. And then at some point, when we get to the node here, we're going to be interested in that, we get to this node, it goes to 0, because that's what happens on nodes. And then as we continue down toward the xy plane past that node, it's going to be non-zero again and rise up as we approach this smaller torus in the xy plane, smaller that is than the big lobes that extend up along z and down along minus z. Okay, so let's represent that graphically. Coming down in theta from theta equals 0 to some value here. We're going to be interested in just what that value is. And then rising up again to theta is equal to pi over 2. Okay? Do you see that? So this is another way of displaying this property. So this is at constant r. And varying theta. Okay. First of all, how can we find out at what value theta goes to 0? Well, we look up here at the functional form of the dz squared. So we get nodal properties of dz squared. We can pretty quickly see that in each of these we've got a factor leading out in front, which is a normalization factor that assures us that the square of the sum integrated over all space of this wave function will come out to be 1. So that if there's an electron in that orbital somewhere, the probability of finding that electron somewhere in space will be 1. So we have these normalizing constants out in front that allow for that and ensure that that is the case. But where we actually find the angular dependence is in that second term. And here it's 3 cosine squared theta minus 1. And what we want to do is say, okay, when does this function go to 0? Because when that goes to 0, we'll have this angle here. So if we let this equal 0, we're looking for the value of the angle theta, which corresponds to the node of the dz squared orbital. And remember, I mentioned this last time, because of the cylindrical symmetry of the dz squared orbital, this really is a conical nodal surface that's above and below the plane here. So if you're anywhere on that cone, either in plus or minus z, the value of that dz squared orbital is 0. Okay? And so we're setting it equal to 0 to find the angle theta. And we can rearrange this and say that cosine squared theta is equal to 1 over 3. And if we go ahead and solve that, this comes out to the arc cosine of root 3 over 3. And the other possibility that satisfies that relation is pi minus the arc cosine of root 3 over 3. And so what that means is that this relation here gives us the angle for that cone in the plus z axis. And then this one down here, pi minus arc cosine root of 3 over 3, gives us the angle for that cone down in the minus z axis. Okay? And what is this? This is, in degrees, something like 476 degrees approximately. Okay? 54.476 degrees. So that's just how far down you are from the z-axis when you hit that nodal surface of z. And that number, you're going to see, is kind of a magical number in chemistry. And it'll harken back to some of the things that we've been talking about recently. And in order to get to that point, I'm going to need to now talk about our ligands again with respect to dz squared. Okay, we're considering now an octahedral metal complex. This is the type of Werner-esque complex that we talked about last time. And you're going to see that we're going to have ligands. We're not really specifying them. We're numbering them and locating them at positions 1, 2, 3, 4, 5, and 6 relative to our metal center at the middle. Okay? And what you might begin to realize is that in order to find out what our energy level diagram will be that refers only to the 5d orbitals on the cobalt center or whatever metal center is at the middle of this ion, what we're going to have to do is evaluate the square of the wave function at each of these ligand positions. And we're assuming that all the ligands are equivalent. If you think of the ligand as an electron or as a point charge in space, then you can imagine that if we have an electron in dz squared up here, that it's going to interact strongly with a point charge and very repulsively with a point charge that would be located at position 1. Okay? Whereas if we instead had a point charge located at that theta angle of 54 point whatever over there that we solved for, then since that's on the node of dz squared, that would be the least possible repulsive interaction that you could get between an electron and an electron in dz squared because it's on the node. Okay? And so what we'd like to do is to go ahead and solve for some of these things. And essentially what we seek energy level diagram. And so let's write this up here. This is 5 over 16 pi. This is dz squared that I'm writing up. 3 cos squared theta minus 1. Okay, and because we're talking about the probability density of finding an electron at a particular point in space, which will mean a particular theta value in our case for dz squared, we're talking about that wave function squared. What we need to do is evaluate it. All right, we've already evaluated it where the node is, but we'd like to evaluate it at position 1. Okay, because we've got a ligand at position 1, and we need to know what the relative response will be of dz squared to a ligand along position 1 versus the other 5 positions. We can say something about that by symmetry already, and so we're going to find out that the value that you get for evaluating dz squared at position 1 is the same as you would get for evaluating it at position 6. Okay, and that's because the big lobes of dz squared are along plus and minus z. That's where ligands 1 and 6 are. And then because the torus is also cylindrically symmetric, 2, 3, 4, and 5 have the same value when you evaluate dz squared at those positions. Okay, but that value is smaller than along z, as illustrated by this graph over here, but we just want to know how much smaller. And so, let's see here. Good. So this is position 1. We get a value of 5/4. And down here, position 2, a value of 5/16. I'm leaving off a factor of pi. Please don't be concerned by that. But these are the relative values that you get when you evaluate this function at ligand positions 1 and 2, which is all we need to do because of the symmetry of this, because that value for position 1 is also true for position 6. All right, so we have positions 1 and 6. And then this is also 3, 4, and 5. So by doing 2 quick evaluations at 2 different theta positions, position 1, of course, theta is equal to 0 up here, and we evaluate that squared function for theta equals 0, and we get 5/4 pi, but I'm leaving off the pi. And down here at position 2, we evaluate this for theta equals pi over 2, okay, because we're down on 2, 3, 4, and 5 are all in the xy plane at 90 degrees to z. So the value of theta anywhere for those 4 ligands would be pi over 2. You evaluate this function for pi over 2, and you'll get 5/16 pi, and I've just left off the pi. Okay? So that's useful. And then let's take this one up to the top. Now next, so here we've done one of the d orbitals. This is dz squared for all 6 ligand positions. All right, and now let's do d x squared minus y squared for all 6 ligand positions. Okay, first of all, dx squared minus y squared has a pretty interesting relationship with ligands 1 and 6. What is that relationship? This is positions 1 and 6. 0, okay, because x squared minus y squared has 2 nodal surfaces that intersect along the z-axis. And so those ligands, 4 and 6, lie on a nodal surface, and so we know that that is going to be equal to 0. If, however, we go ahead and evaluate the square of dx squared minus y squared, let me just write it up, and I have to switch it since they're wrong in the book. 15 over 16 pi square root sine squared theta cosine 2 phi. Okay, we have that. And now, just as we do, we're converting an orbital angular property into a probability density by squaring it. This is what we normally do. When you see pictures of orbitals, they're representing the square of the wave function in space. And so we need to evaluate this as a function of theta and phi in order to find out what's the first 2, 1 and 6, we did by inspection. But what about positions 2, 3, 4, and 5? In the case of those 4, you can see that where they lie in the xy plane with respect to the x squared minus y squared orbital is all identical to each other by symmetry, because x squared minus y squared has lobes that extend along x and plus x and y and minus y, and that's where all these ligands lie at positions 2, 3, 4, and 5. We know that theta is equal to what? It's going to be pi over 2, and phi, of course, can be 0, pi over 2, pi, and 3 pi over 2 for any of those positions. And what we'll find is that this evaluates for any of those. Let's just use phi equals 0. Okay, evaluates as 15 over 16 pi, and I'm dropping the pi. Okay, so now we've got dz squared and dx squared minus y squared evaluated for all 6 ligand positions. And then let's make a table of this. dz squared, x squared minus y squared. Let's do xz, yz, and xy. Okay, and here's our ligand positions. And in the table here, we're going to put what these relative evaluated squared wave functions are. And the biggest one of all is this one here that we got at position 1 for dz squared, which is 5/4. So I'm going to divide everybody through by 5/4 so that I can make our biggest value equal to 1. Okay, for simplicity here. And then when we do that, you're going to see that 2 gives a value of 1/4. That's position 2 down in the torus. 3 down in the torus is 1/4 relative to that 1. 4 is 1/4. 5 is 1/4. And 6 down in minus z is 1. Okay? So we've evaluated the dz squared orbital squared at the ligand positions 1 through 6, and these are the relative values that we got for the probability of finding an electron at that point in space given a constant value of r. And x squared minus y squared, we got for positions 1 and 6, 0. We just said that. And then on the same scale here, we get 3/4, 3/4, and 3/4. And then for xz and yz and xy, this is now we've gone through these 2 steps to do z squared and x squared minus y squared explicitly. Now we have to look at where ligands 1 through 6 are relative to the nodes of xz or yz and xy. And what we will find is that in each case, these ligands lie on nodal surfaces of xz, yz, and xy. So this is 0, 0, 0, 0, 0, 0, 0, 0, and so on. Okay? So all the ligands 1 through 6 lie on nodal planes of xz, yz, and xy. Only 4 of the ligands interact with x squared minus y squared. Ligands 2 through 5, because those are the ones that lie in the xy plane. And they interact strongly, this relative value of 3/4, but not as strongly as the 2 ligands in positions 1 and 6 interact with the big lobes of dz squared. And then also ligands 2 through 5, which lie in the xy plane, interact with the torus of dz squared, but to a much smaller extent because the torus does not have as great a radial extent, and these ligands are all at the same radius out from the metal center. And so what this corresponds to is now an energy level diagram as follows. And this is for an octahedral complex. Where we have relative energy units of 0, 1, 2, and 3. And what we have to do is say that the amount an electron in dz squared would be repelled simultaneously by electrons in positions 1 through 6 would be the sum of these values. And so we add that up, and we get, in fact, for dz squared, up here, a 3. And interestingly, for dx squared minus y squared, if we take a sum of the 4 interactions that we found that are non-zero, we also get a 3 for dx squared minus y squared. So then the net of all their interactions is the same for x squared minus y squared and z squared. And then down here, we found that these 3 orbitals, xz, yz, and xy, where the ligands at positions 1 through 6 lie on their nodal surfaces, lie right on their nodal surfaces. And so the number evaluates to 0. So a wave function squared will evaluate to 0 anytime you're looking at a position that's on one of its nodal surfaces. It evaluates to 0, and so we have dxz, dyz, and dxy. And then a diagram like this, which is a d orbital splitting diagram, is associated with a couple of different parameters. One is, down here we've got a triply degenerate energy level. Previously we'd only seen doubly degenerate energy levels. Now we've got a triply degenerate one composed of xz, yz, and xy. And that level we're going to be calling T2G. And then up here we have a doubly degenerate level that will get the label EG. And whatever the value of the splitting of these two energy levels, one triply and one doubly degenerate, we're going to give that the label delta O for octahedral. Okay? And at the beginning of next hour, I'll say more about tables like this, and I'll show you how you can actually figure out d orbital splitting diagrams for other coordination geometries and how they compare for a couple of the most popular coordination geometries.